This is lecture 4J, and today we're going to revisit the topics of empirical and molecular formula calculations. Our first example, when a sample of a hydrocarbon is burned, 8.45 grams of carbon dioxide and 1.73 grams of water are produced. Calculate the empirical formula of the hydrocarbon. This example looks a little bit different than the previous empirical formula determination problems we've seen. Usually in a problem, I tell you a compound is known to be 80% carbon and 20% hydrogen by mass. What is its empirical formula? In this case, I'm giving you more raw data. Where did they get the 80% and the 20%? Well, usually it comes from burning the particular unknown hydrocarbon. When you burn something, that means you're reacting it with oxygen. So if we have an unknown hydrocarbon, which I can represent as CXHY, when that's burned or combusted, the oxygen actually reacts with both the carbon and hydrogen, forming carbon dioxide and water. Experimentally, what chemists can do is they can actually place this unknown hydrocarbon in a furnace and pass oxygen into it. That will cause the combustion to take place in the furnace. The product gases, the carbon dioxide and the water vapor, are then passed through two separate chambers. One of them contains the compound magnesium perchlorate, which is an absorber of water vapor. So if the mass of the magnesium perchlorate is weighed before the burning is done, and then the water vapor passes over it and is absorbed and then is weighed again, you can actually measure the mass of water that was released from this combustion, which in this case is 1.73 grams. The vapor is also passed through another container that contains sodium hydroxide, which is an absorber of carbon dioxide. So if the sodium hydroxide is weighed before the reaction occurs and then weighed afterward, the difference is going to tell you how much carbon dioxide was produced, and in this case, it's 8.45 grams. So with that in mind, here's how we can calculate the empirical formula of this compound. If we know 8.45 grams of carbon dioxide was produced, we can figure out how much carbon must have been produced, and that's therefore going to equal the amount of carbon in our original compound. Why is that the case? Because the carbon in our original compound only went into the carbon dioxide. The amount of carbon in the CO2 has to exactly equal the amount of carbon in the original unknown hydrocarbon. So how do we figure out how much carbon is in CO2? Well, if you calculate the molar mass of carbon dioxide, the molar mass of carbon dioxide contains 1 mole of carbon, which weighs 12 grams, and the entire molar mass of carbon dioxide you can calculate to be 44 grams. So the fraction 12/44 is how much carbon is in CO2. So if I think about my calculation for molar mass and just do the fraction of carbon in the CO2, I can cancel out my grams of CO2, and I now know how many grams of carbon must have been in the carbon dioxide. That comes out 2.306 grams. And if that amount of carbon is in the carbon dioxide, that has to exactly equal the amount of carbon in our original hydrocarbon. We're going to use a similar technique to calculate the amount of hydrogen in our unknown hydrocarbon. If we produced 1.73 grams of water, where did all the hydrogen in the water come from? The hydrogen had to come from the hydrocarbon. That's the only source of hydrogen on the reactant side. So the amount of hydrogen in water here is exactly equal to the amount of hydrogen in the original unknown hydrocarbon. So calculating the molar mass of water, we know it weighs 18.02 grams per mole. Well, how much of that is hydrogen? It's 2 times 1.01 or 2.02. So if I take the fraction 2.02 out of 18.02, that's the fraction of water in which hydrogen is responsible for. Arrange it this way so the grams of water cancel out. This is now how many grams of hydrogen are in the water, and therefore that's how many grams of hydrogen must be in the unknown hydrocarbon that we started with. So if you can determine the mass of each of the elements in the compound that you're trying to get its empirical formula, now it becomes a more elementary empirical formula determination. Usually, if we're given percents, the first thing we do is we assume you have 100% of the compound, and therefore the percents become the mass or the grams. Well, here we've just calculated the actual number of grams of carbon and hydrogen in the unknown. So now we go to step 2. Once you have the masses of the elements making up the compound, convert them into moles with their molar masses. So I'm going to convert the 2.306 grams of carbon into moles with carbon's molar mass, and that comes out to be 0.192 moles of carbon. Then I'm going to do the same thing with hydrogen. I'm going to use hydrogen's molar mass to convert the grams of hydrogen into moles. This comes out 0.192 moles of hydrogen. Once you've calculated the moles of each of the elements in the compound, the mole ratio between those elements is the same as the atom ratio for the compound. This one we can actually see. If we divide them both by 0.192, this comes out a 1-to-1 ratio. So this particular compound has 1 mole of carbon to every 1 mole of hydrogen, which means it has 1 atom of carbon to every 1 atom of hydrogen. So the empirical formula must be CH. Let's try a second example. A borane is any compound composed of boron and hydrogen. When a sample of a borane is burned, 12.89 grams of B2O3 and 12.27 grams of H2O are produced. Calculate the empirical formula of the borane. So once again, I'm giving you raw data from an experiment dealing with this unknown compound, as opposed to telling you the compound is 60% boron and then 40% hydrogen. So we have to think about what reaction is occurring and where do these numbers come from. If you take a borane and you combust it or you burn it, that means you react it with oxygen. So if I don't know the formula, I'll represent it as BXHY. If I combust it or burn it, what happens in a combustion reaction is the oxygen forms compounds with both elements in your compound being burned. So you're going to form a compound between boron and oxygen, that must be the B2O3, and you form a compound between oxygen and hydrogen, that must be H2O. And if we can measure the amount of boron in the B2O3, that's exactly how much boron is in the original borane. If we can measure how much hydrogen is in the water, that's going to exactly equal the amount of hydrogen in our original borane. So we'll be able to get the masses of the two elements and then determine its empirical formula. So if we start with 12.89 grams of B2O3 and think about how you calculate the molar mass of B2O3, it would contain 2 moles of boron, and that would be 2 multiplied by 10.81. And we divide that by the molar mass of the entire compound, which happens to be 69.62 grams per mole. So out of the 69.62 grams per mole of B2O3, 21.62 grams of it are boron, because again, there were 2 moles of boron in the formula, so it'd be 2 multiplied by boron's molar mass of 10.81. This comes out to be 4.0029 grams of boron in the B2O3, and that is therefore how much boron is in our unknown borane. The 12.27 grams of water are going to allow us to calculate how many grams of hydrogen are in our unknown compound, because we can determine how much hydrogen is in the 12.27 grams of water. 1 mole of water weighs 18.02 grams, and out of that 18.02 grams, 2.02 grams of it is due to hydrogen. So if we multiply by this ratio, 18.02 grams of water to 2.02 grams of hydrogen, we can convert the grams of water into grams of hydrogen. And so our water contains 1.375 grams of hydrogen. And because all the hydrogen came from the borane, that's going to exactly be how much hydrogen is in our unknown compound. So once you have the masses of each of the elements that make up your unknown compound, now the empirical formula determination is just like we had done previously. We take the masses of the two elements and we use their molar masses to convert them into moles. So using boron's molar mass, we can calculate that the 4 grams of boron is really 0.37030 moles of boron. And then the 1.375 grams of hydrogen, using its molar mass to convert it into moles, will tell us that this sample is 1.361 moles of hydrogen. And then once you have the moles of the two elements, the simplest mole ratio between those two elements is going to be the same as the atom ratio. So I'm going to take the moles of boron and the moles of hydrogen and divide them by whichever is the smallest number, which is the 0.37030. Doing that, I get exactly 1 mole of boron, but I get 3.67 moles of hydrogen. That number needed to be within 1/10 of an integer, so 1/10 of the number 4, for us to assume that the ratio is 1 boron atom to 4 hydrogen atoms. So it therefore is not. So what we have to do is then we have to multiply these two numbers by 2 to see if they'll make integers, which they don't. But if we multiply them both by 3, they actually do come out to be integers. That comes out to be 3 moles of boron to really close to 11 moles of hydrogen. And so therefore the empirical formula for this compound would be B3H11. In this example, when a 3.84 gram sample of a compound containing carbon, hydrogen, and nitrogen is combusted, 7.34 grams of carbon dioxide and 2.41 grams of water are collected. Calculate the empirical formula of the compound. This is a little bit different than the previous two problems because this unknown compound has 3 elements in it. So we'll show you how you handle a situation where the unknown compound contains 3 elements, but you're given raw experimental data. So this compound would have the formula CXHYNZ because I don't know how many atoms of each are in the formula, and that's what we're trying to figure out. If you combust it, you're going to get an oxide of carbon, which will be CO2. They talked about that in the problem. An oxide of hydrogen, that's going to be H2O. They talked about that in the problem. And the oxygen and the nitrogen are probably going to combine to form a third compound, but they didn't tell us what it was, and they didn't tell us how much. So that's unknown, but it had to have been formed. We had to have a third product in that chemical reaction. Even though we weren't given information about that third product, we can still determine the empirical formula, and here's how we're going to do that. If you take the 7.34 grams of carbon dioxide, like we've done in the previous problems, you can calculate the amount of carbon in the CO2 by using the molar mass calculation and using the fraction of the compound's mass that is carbon over the molar mass. So there's 1 mole of carbon in CO2, which weighs 12.01 grams, and 1 mole of carbon dioxide weighs 44.01 grams. That fraction, if you multiply by the 7.34 grams, will tell you how much of the 7.34 grams of CO2 is carbon, and that comes out 2.003 grams. The water information, like we've seen in both the last problems, can be used to calculate how much hydrogen is in the water and therefore how much hydrogen is in our unknown compound, because water is 2/18 hydrogen, so 2.02 grams of hydrogen out of the 18.02 grams of water will tell us how many grams of hydrogen are in the water. That comes out 0.2814 grams of hydrogen. This is therefore how much hydrogen is in our original compound. Now, how are we going to get the nitrogen information? Well, they gave us one more bit of information that's really significant. They actually weighed out the sample before they combusted it. If the sample weighs 3.84 grams, and that's the mass of the compound of carbon, hydrogen, and nitrogen, and we've just figured out how much of that is carbon if we subtract out 2 grams from that, and we know how much is hydrogen if we subtract out the mass of hydrogen, we're getting rid of all of the carbon and all of the hydrogen in the compound. What's left over? It has to be the mass of the nitrogen. So by subtraction, we can determine that this unknown compound must have contained 1.5556, and then 1.56 to the right significant figures, grams of nitrogen. So we now know the masses of all 3 elements that make up the compound, and you need to be able to determine the masses of the 3 different elements in the compound if you want to get its empirical formula. So we take the masses of the 3 different elements, and just like before, we're going to convert the masses of each of these into moles and then divide them by the smallest number. So using carbon's molar mass, we can determine that this sample contains 0.1668 moles of carbon. Using hydrogen's molar mass, we can determine that this sample contains 0.2786 moles of hydrogen. And then using nitrogen's molar mass, we can determine that this sample contains 0.1110 moles of nitrogen. So once you have the moles of all 3 elements, we divide them all by the smallest number and see what the simplest ratio is. And 0.1110 is the smallest of the 3 numbers. So if I rewrite the numbers again and now divide them all by 0.111, I'm going to get a simple ratio for at least one of them. This comes out to be 1.50 moles of carbon, 2.51 moles of hydrogen, and 1.00 moles of nitrogen. So the nitrogen's an exact integer, but the carbon and hydrogen values are not within 1/10 of an integer. In fact, they're really close to 1.5 and 2.5. And if you can recognize that, that means you need to multiply every single one of these number of moles by 2. If you do that, you'll get 3 moles of carbon, just barely over 5 moles of hydrogen within the range of plus or minus 0.1, and then 2 moles of nitrogen. So the empirical formula would be C3H5N2. When a 2.75 gram sample of a compound containing carbon, hydrogen, and oxygen is combusted, 5.49 grams of CO2 and 2.25 grams of water are collected. Calculate the empirical formula of this compound. So this is almost identical to the last compound where there are 3 elements in the unknown, but they're only giving you the masses of 2 products, the carbon dioxide and the water. If you wanted to pause and try to do this calculation on your own, you may do so, and then I'll start doing the calculation once you're ready. When you combust a compound of carbon, hydrogen, and oxygen, the oxygen will combine with the carbon to make carbon dioxide. The oxygen will combine with the hydrogen to make water, and there actually is no compound formed between oxygen and oxygen, so there actually isn't even a third product. There's only these 2. So they actually gave you all the data of the combustion reaction of our unknown compound. The 5.49 grams of CO2, we can use that to calculate how much carbon is in the CO2 by multiplying it by the fraction of carbon in 1 mole of CO2. And that comes out 1.498 grams of carbon. And because all that carbon came from our unknown compound, the 1.498 grams of carbon must be the amount of carbon in our original unknown. The 2.25 grams of water can be used to determine the mass of hydrogen in the water by using the fraction of water's molar mass that's hydrogen, which is 2.02 grams out of 18.02 grams. We can calculate the mass of hydrogen in the water, 0.2522 grams, and because all the hydrogen came from our unknown compound, that must be how much hydrogen is in our unknown compound. The only element we can't get directly is the mass of oxygen, but we do that by subtraction. If we know that the mass of the compound that was burned was 2.75 grams, and we've now calculated how much of that is carbon and how much of that is hydrogen, we just have to subtract those, and we're going to get how much is left over, which has to be the mass of oxygen. So if we subtract the 1.498 grams of carbon and the 0.2522 grams of hydrogen, that actually cancels out the carbon and cancels out the hydrogen. So mathematically, you're calculating how much oxygen must be in the compound. And by subtraction, that comes out to be 0.9998 grams of oxygen. Now we know the masses of all 3 elements in the compound. We can use those masses to convert into moles, divide by the smallest number, and then calculate our empirical formula. So taking the mass of carbon and using carbon's molar mass, we can determine that this particular sample contained 0.1247 moles of carbon. Using the molar mass of hydrogen, we can determine that this sample must have contained 0.2497 moles of hydrogen. And then using the molar mass of oxygen, we can determine that this sample must have contained 0.06249 moles of oxygen. And now that we have the moles of all 3 elements, we're going to divide them all by the smallest number, which is 0.06249, and see what simple ratio we get. When we divide each of these numbers of moles by the smallest number, I get 2.0 moles of carbon, 4.0 moles of hydrogen, and 1.0 moles of oxygen. These are all exact integers, and so this mole ratio becomes exactly the atom ratio. The empirical formula must be C2H4O. Now, 5.48 grams of the compound that we just determined its empirical formula for are dissolved in 78.0 grams of benzene, who has a freezing point of 5.5 degrees Celsius and a molar freezing point constant of 5.12 Celsius degrees kilogram per mole, and the resulting solution freezes at 1.5 degrees Celsius. Calculate the molar mass of the compound. So this is a colligative property data involving freezing point of a solution. We've dissolved 5.48 grams of this unknown compound in 78 grams of benzene, and the freezing point has gone from 5.5, or rather gone from 5.5 down to 1.5. we can calculate from a change in freezing point or any of the colligative properties the molar mass of the compound. Comes from our colligative property equation. Change in freezing point equals freezing point constant multiplied by molality times I. We know the grams of the compound that were dissolved into the solution. That's the first number in the problem, 5.48. We need to calculate how many moles of the compound must be in the solution, so we use the colligative property equation to calculate moles. To do that, I replace molality with its actual definition of moles per kilogram, and I can calculate what the change in the freezing point is because the freezing point went from pure benzene's 5.5 down to the solution's freezing point of 1.5. That's a difference of 4.0. So replacing molality with moles per kilogram and then solving this equation for moles of solute, I know every other number in the problem, we can determine how many moles of solute there must be. So the moles of solute will equal the kilograms of the solvent, and that's the benzene. There were 78 grams of benzene, so that would be 0.0780 kilograms. Delta T sub F is 4.0. K sub F is 5.12. And the I value for this compound, it wouldn't dissociate or ionize in benzene because that's a nonpolar solvent, so it must be a value for 1. So plugging the numbers into the equation, we can cancel out the kilograms, cancel out the Celsius degree, and we're going to wind up getting moles as our only units as they flip up to the numerator. So therefore, we've determined that this sample must have contained 0.0609 moles of this solute. By knowing the mass of the solute we dissolved and dividing it by the moles of the solute, that's going to wind up being the molar mass of the solute, and that comes out to be the two significant figures, 90 grams per mole. So we've calculated the empirical formula of this compound from colligative property, and that was from combustion data. We calculated the molar mass of the compound from colligative property data. The final thing we can do now is we can calculate the molecular formula of the compound. You can always do that if you have the empirical formula and the molar mass. So the way you calculate the molecular formula of the compound is you go back to its empirical formula and you determine the molar mass of the empirical formula. This in particular formula has 2 moles of carbon in it, it has 4 moles of hydrogen in it, and it has 1 mole of oxygen in it. So if you add that up, that's going to be the molar mass of your empirical formula, and that turns out to be 44.06 grams, or grams per mole. If the compound's actual molar mass was 90 grams per mole, you take 90 grams per mole and you divide it by 44.06, and that number has to come out close to an integer. May not be exact because the data may not be great, but it's going to be close, and this actually does come out really close to 2. That means the real molecule must be twice as big as the empirical formula. That's the only way the mass can be 90 instead of 44, and so the molecular formula is C4H8O2. So that concludes our information for our 4th exam. Let me go through some things that you want to make sure you're prepared for exam 4. You're going to want to make sure you understand and can use the solubility rules that are listed on handout 6. You'll need to be able to calculate oxidation numbers because those are used in balancing non-obvious oxidation reduction reactions. And you should definitely know the definitions of oxidation and reduction. And you should know the definition of an oxidizing agent and a reducing agent. And specifically, there are 4 oxidizing agents that we talked about that are listed on handout 6 that you should be familiar with and know what they get reduced into. Then a large portion of the test will be you writing balanced chemical equations. And for all the types of chemical reactions we've talked about, which are combustion, replacement, composition, decomposition, the different types of exchange reactions that form precipitates, waters, or gases, and then the 2 non-obvious reactions, the Bronsted acid-base and the non-obvious oxidation reduction reactions. For each of those, I would like you to be able to predict if a reaction would occur if I give you some reactants, be able to predict what the products are for the chemical reaction, write me a balanced equation, and then if it's a reaction that occurs in water solution, give the net ionic form for those water solution reactions. Second part of the test was on the stoichiometry of chemical reactions. And so I'll expect you for a chemical reaction to be able to give me the mass of a particular reactant or product, or give me solution data for a particular reactant or product. So chemical reaction calculations, where you're either given masses or solution data, be able to solve for amount of any other reactant or product in the chemical reaction. The keys for this were, if you're given mass data, you have to be able to convert that into moles, and that's done with a molar mass. If you're given solution data, you have to be able to convert that into moles, and that's done by multiplying molarity times volume. I'll expect you to be able to do a limiting reactant calculation, where I'm not just giving you the amount of one reactant and you assume it all reacts away. I'm going to give you 2 or more reactants, and then you'll have to do an ICF table, figure out which one gets reacted away completely, and then how much of the product is produced. We talked about how you get ion concentrations in mixtures. So I'll give you problems where we'll mix solutions together, and I'm going to say, what's the concentration of the ions in that solution after any reaction may have occurred. You need to know how to do a dilution calculation, so you should know the dilution equation. And then we talked about a technique we use to actually react substances in solution with each other. Those are called titrations. They're usually either acid-base titrations or oxidation reduction titrations. And in a burette, we usually add one reactant to another until we have them exactly reacted with each other stoichiometrically. And we usually tell when that happens by using a substance called an indicator, which changes color once the reaction is ended. We defined a standard solution, which is a solution of known concentration. And then we spent one day doing conversions between masses, moles, and then either atoms or molecules. So you'll have some calculations like that. Today, we talked about molar mass calculations, which are fairly elementary. We've been doing that for quite a while. And today we also talked about, percent composition calculations, as well as empirical and molecular formula calculations. Those are the ones we actually did today. You should be familiar with chapters 4 and 5, and the experiments that you will need to know, because questions will come from them, are experiments 15 to 20.